Hello. On this video, we're going to go over some simple examples of exponential functions. The first thing that we're going to notice is that the variable is now on the exponent, and this value right here, the 2, is known as the base, sometimes represented by a b. So this is a base 2 exponential function. And every input, every x value is going to end up as the exponent of that base, of that 2. So if we evaluate the function h with an input of -2, that means that this function is going to take a -2, and that -2 is going to end up as the exponent of the exponential. So that is going to end up making f of -2 equal to 2 raised to the power of -2. Anytime you raise a number to a negative exponent, that means that because of laws of exponents, this is equivalent to having 1 over 2 raised to the power of 2. And in this case, this is going to be 1 over 4. So that's just using laws of exponents. So this first value is 1 over 4. Then if you use -1, you're going to do the same, f of -1. Now, -1 will end up as the exponent. And this is, because of laws of exponents, this is equivalent to 2 raised to the power of 1, or 1/2. So that next value is 1/2. Next, we have f of 0. So that is 2 raised to the power of 0. Any value, any expression raised to the power of 0 will be equal to 1. So no matter what the base is, if you don't have anything else going on the exponential, meaning a multiplication, is going to go through the point 0, 1, because no matter what the base is, when you raise that base to the power of 0, you will end up with a 1. Just bear in mind that you can have sometimes a coefficient or a value multiplying the exponential expression. Then we're going to do f of 1, and in this case, it'll be just 2 raised to the power of 1. That's 2. And f of 2 will be 2 raised to the power of 2. That's a 4. So if you plot those coordinates, I'm gonna do my best. The first one is -2, 1/4. So that's gonna be very close to 0. Then -1, 1/2. Then 0, 1. Then 1, 2. And 2, 4. So this will give us an idea, and this is something that you should know. The first value that we're using is -2, but we could be using -12 or -1000. No matter how big the value is, we'll never reach 0. So let's say that we have f of -1000. So that's gonna make this 2 raised to the power of -1000. So that's gonna be 1 over 2 raised to the power of 1000. That is gonna be very close to 0, but never reaching 0. So the more you move closer to plus and minus infinity, or to the left, the closer you're gonna be to 0, but never actually reaching 0. So that brings an asymptote. This asymptote will only be approached by the exponential, but never actually reaching this asymptote. If we don't have any transformations, vertical shifting, horizontal shifting, reflections, any of those things, the graph will have a horizontal asymptote at 0. And the graph will look something like this. We have to connect the dots, and it'll be an exponential growth. So this will keep going up. So we could find a few more points, and this will keep approaching the horizontal asymptote without ever reaching it. So in this case, the domain of the function is, if you notice, we can use pretty much anything that we want, any x value, so that will make this a domain going from minus infinity to infinity. And the range is going to be restricted by the asymptote. In this case, the asymptote is at 0. So the graph goes from 0 to infinity. Now, if you notice, the negative exponents in a way change the way this is behaving. So let's go to the next example where we have a similar example, but in this case, we're going to have a fraction. So if we have a fraction, we're going to do the same, but you're going to notice that this will make the graph reflect in a way. So this is equal to, because of loss of exponents, you can say that 1 over 2, 1/2, is 1 divided by 2 raised to the power of 1. If you remember from the previous example, this was the same as 2 raised to the power of minus 1. Those two are equivalent expressions. So this can be expressed as 2 raised to the power of minus 1 raised to the power of x. So basically, this can also be expressed as 2 raised to the power of minus x. So that's up to you if you want to use it in this way or as a fraction. Both will get you the same answer. Let me show you. If you do f of minus 2, you're going to end up with 2 raised to the power, or let me do the fraction first, 1/2 raised to the power of minus 2. And this will get you, because of loss of exponents, this will be 1 raised to the power of minus 2 and 2 raised to the power of minus 2. So because of loss of exponents, we're going to end up with 2 raised to the power of 2 divided by 1 raised to the power of 2, and that's going to be 4 divided by 1. So that's a 4. So if you notice, it's pretty much if you were to raise this to the power of 2, but you have to flip the fraction. Or if you do it considering this version of the function right here, you would end up having f of minus 2, and you already have 2 raised to the power of minus, and you're going to have to input a minus 2. So this will end up as 2 raised to the power of positive 2. So that is also a 4. So it's up to you. How do you want to do it? Just remember the loss of exponents. And then in this case, we're going to have f of minus 1, and I'm going to use this version. So that's going to be 2 raised to the power of minus 1. So that's 2 raised to the power of 1. That is 2. And then, as I said before, any value raised to the power of 0 is going to be 1. So this, if the input is 0 and you don't have anything multiplying your exponential expression, you'll get a 1. And then I'm going to use the fraction. So that's f of 1 is equal to 1/2 raised to the power of 1. That's 1/2. And finally, we have f of 2 raised to the power of 1/2 raised to the power of 2. So that's 1 squared, that's 1. 2 squared, 4. I don't know if you remember this from the previous example. Let me go back. But the previous example, you had something like this. So we had 2 raised to the power of x. Now we have 2 raised to the power of minus x, or 1/2 raised to the power of x. So if we sketch this, you're going to end up with something like this. So this is 1/2 raised to the power of x, or 2 raised to the power of minus x. And at minus 2, you're going to be at 4. Then at -1, you're going to be at 2. 0 is still a 1. Then 1 is 1/2, and 2 is 1/4. We're still going to be approaching a horizontal asymptote at 0, like this. And the graph, let me see if I can at least do a decent job, is going to approach the asymptote, and it's going to come something like that. So this is going to continue growing and continue approaching the asymptote. But I don't know if you remember, this one right here is 1/2 raised to the power of x. The one that we had before, it was a reflection. At 1, we had a 2. At 2, we had a 4. And here we had, at -1, we had 1/2. And at -2, 1/4. So the graph looked like this. And this is 2 raised to the power of x. So whenever you have a negative exponent and the base is the same, you're going to end up having a reflection over the y-axis, over this x-axis. But later on, we're going to do it with transformations. Right now, we're just evaluating the function and trying to figure out how the graphic will look. So those are the two functions. And finally, I want to show you something else. So here, this one is a graph with a transformation. Just like transformations, I don't know if you remember, if we had f of x equals x squared plus 1, that meant a vertical shifting. And if you had f of x equals x minus 1 squared, that meant a horizontal shifting to the right. Exponential functions also have transformations. If you have f of x equals 2 raised to the power of x plus 1, that means that the horizontal asymptote is going to be shifted 1 unit up. So instead of having the horizontal asymptote at 0, we're going to have it at 1, and the graph will be shifted 1 unit up. And if you have, let's say, f of x equals 2 raised to the power of x minus 1, everything as the exponent, that is going to shift your graph 1 unit to the right. So if you recall, all graphs pass through the point 0, 1. So the original graph goes like that. The shifted graph is going to be 1 unit to the right. So it would look something like that. So that's a general idea. Later on, we're going to do the shifting using the kind of like the function we already saw. We already know how 2 raised to the power of x looks like. So that graph can be shifted. So this one, in order to find the domain, well, the domain of an exponential will always go from -infinity to infinity. The range is the one that we have to be a bit more careful with. So this is going to go from -infinity, the domain, to +infinity. But this one, the horizontal asymptote, originally on the parent function is over the x-axis. So that means that the graph was shifted 2 units up. So you had a function, we don't know the exact function, but it's f of x equals the base raised to the power of x. And we know that at least was shifted 2 units up. There could be a horizontal shifting. Looks like there's a horizontal shifting, but we're not going to worry about that right now. So because it was shifted 2 units up, and now we have the horizontal asymptote at 2, the range will go from +2 to infinity. So this will allow you to do a few problems from the activity. So give it a shot, and later on we will see a bit more about this topic.